Section: Introduction. In this section, we will discuss diffusion models, which have become popular for generating images, videos, and audio. One drawback of diffusion models is that they are slow when it comes to generating samples compared to training. While training only needs one function evaluation per data point, generating a sample can require many evaluations. Recently, consistency models have improved sampling speed, but at the cost of image quality. Consistency models come in two types: consistency training, CORT, and consistency distillation, CD, both showing better performance than earlier methods. Tract focuses on distillation and suggests that dividing the diffusion process into stages can enhance performance. However, neither consistency models nor Tract achieve the same performance as a standard diffusion model. To bridge this performance gap, we propose a combination of consistency models and Tract. We relax the single-step constraint in consistency models, allowing up to 4, 8, or 16 function evaluations in certain cases. We extend Tract to consistency training and incorporate step schedule annealing and synchronized dropout from consistency modeling. As the number of steps increases, multi-step CT behaves like a diffusion model. Our unified training algorithm, called Multistep Consistency Models, divides the diffusion process into segments, each trained by a separate consistency model sharing the same parameters. This approach improves performance significantly with fewer steps. Surprisingly, we achieve performance comparable to standard diffusion models with just 8 steps on ImageNet 64 and ImageNet 128 datasets. Additionally, we introduce a deterministic sampler named Adjusted DDIM, ADDIM, for diffusion models, which performs well on complex datasets like ImageNet 128 in terms of FID score. With as few as 8 or sometimes 4 sampling steps, we achieve results comparable to standard diffusion methods in both consistency training and distillation. Notably, multi-step consistency models achieve FID scores of 1.6 on ImageNet 64 and 2.3 on ImageNet 128 with only 4 sampling steps. Moving on to diffusion models, they involve a process that adds noise to data, represented by the equation z_t equals alpha_tx plus sigma_t, epsilon_t, where epsilon_t is a standard normal random variable. The diffusion process transforms z_t from being close to a standard normal distribution for t close to 1 to approximately x for t close to 0. The signal-to-noise ratio SNR-T is defined as alpha_t squared, sigma_t squared, which is crucial for these models. Sampling from diffusion models involves denoising equations and predicting x using a learned function. The optimal solution under a diffusion objective is to learn the expectation of x given the noisy observation z_t. Sampling iteratively for different values of t and s starting from z_1, sim n, 0, 1, is necessary, with the number of steps depending on the data distribution. Diffusion models are computationally intensive, often requiring hundreds of iterations for generative processes like image generation. Section Summary. In this section, we introduce diffusion models as powerful generative models for image, video, and audio generation, highlighting their drawback of requiring many function evaluations for sampling. We discuss consistency models, including consistency training, CORT, and consistency distillation, CD, which have improved performance but fall short of standard diffusion models. By unifying consistency models and Tract, we propose multi-step consistency models that achieve competitive performance with as few as 4 or 8 sampling steps, showcasing significant advancements in image generation tasks like ImageNet 64 and ImageNet 128. Section: Consistency Models. In this section, we discuss consistency models. Consistency models aim to directly map noise to data. They predict x based on z_0 and are trained to be consistent by minimizing certain constraints. These models aim to predict the same x throughout the trajectory. Initially, the model learns near 0 and gradually extends its predictions to t equals 1 during training. training consistency models is more challenging than diffusion models based on our experience. Consistency models come in two types: consistency training, CORT, and consistency distillation, CD. CT uses data to define Z_S, while CD involves using a pre-trained diffusion model as a teacher to guide the learning process. An important aspect of consistency models is the gap between evaluations at different times, which affects the bias and information propagation speed through diffusion time. The DDIM sampler is a linearization of the probability flow ODE used in diffusion models. It serves as a sampling method and a tool for constructing algorithms for multi-step diffusion models. The inverse of DDIM is also useful for parameterizing student diffusion models based on a teacher's sampling procedure. Multi-step consistency models divide diffusion time into segments to simplify modeling. They aim to integrate the ODE integral accurately by minimizing discrepancies. The multi-step consistency loss is generalized by targeting Z_T_step instead of X. This loss can be reparameterized to X space for better interpretability and relation to standard diffusion losses. It is crucial to prevent the model from collapsing to trivial solutions during training. Section Summary. In this section, we discuss consistency models which aim to learn a direct mapping from noise to data by predicting X equals F, Z_0, 0, and minimizing consistency. Consistency models come in two types: consistency training, CORT, and consistency distillation, CD, where CD uses a pre-trained diffusion model as a teacher. Multi-step consistency models split diffusion time into segments, converging to standard diffusion training, and introduce a deterministic sampler called ADDIM to address missing variance issues in DDIM. Section. Many-step CT is equivalent to diffusion training. In this section, we explore the equivalence between many-step consistency training, CORT, and diffusion training. Consistency training focuses on integrating the probability flow over time, while standard diffusion models follow an expectation that changes over time for complex distributions. There are two main reasons why many-step CT converges to a diffusion model. Firstly, at the start of each step, the objectives are the same. Secondly, when the number of steps matches the total steps, each step aligns with the diffusion objective. For consistency training, when we simplify to adjusted DDIM, ADDIM, it reduces to DDIM. In this case, under a well-defined model like a prediction model, the operation from step S to T_step does not change anything and just gives the reference Z_ref, T_step, equals Z_S. Additionally, we observe that Z_T_step equals Z_S. This simplification shows that the distance between the true data point and the model prediction, weighted by W, T, is typical for standard diffusion models. Interestingly, using Euclidean distances tends to work better than squared Euclidean distances for consistency models. This deviation from the standard diffusion approach is beneficial, especially for smaller steps. By fine-tuning many-step consistency models from a pre-trained diffusion checkpoint, we can achieve quicker and more stable convergence. As the number of steps increases, the performance of many-step consistency models approaches that of diffusion models, offering a trade-off between sample quality and duration. Regarding training in continuous time, while diffusion models can be trained by sampling time continuously, we choose to define time on a discrete grid for simplicity. This discrete approach aligns well with training many-step consistency models from pre-trained diffusion models. Our early experiments show that this method works comparably. In the context of distilling diffusion models, we introduce the adjusted DDIM, ADDIM, sampler to address the issue of integration error causing blurry samples. By adjusting the DDIM sampler to increase the contribution of the deterministic noise estimate, we aim to achieve the correct norm for sampling iterates. Empirically, ADDIM shows improved performance, leading to better FID scores. By estimating the posterior variance empirically or analytically, we can effectively update the sampling iterates. The ADDIM update becomes identical to the original DDIM update in the many-step limit. Section Summary. In this section, we explore the equivalence between many-step consistency training, CORT, and diffusion training, where consistency training integrates probability flow through time while diffusion models follow an evolving expectation. The convergence of multi-step CT to diffusion models is explained by the alignment of objectives at the beginning of each step and the equivalence of objectives when the number of steps matches the total steps. Additionally, training multi-step consistency models from pre-trained diffusion models can lead to faster convergence and comparable performance as the number of steps increases, offering a trade-off between sample quality and training duration. Section: Related work. In this section, we discuss related works that are similar to ours, such as consistency models and tract. Our approach differs from consistency models by operating on multiple stages, which simplifies modeling and enhances performance. On the other hand, tract focuses on distillation and utilizes self-evaluation from consistency models to distill models over multiple stages, progressively reducing them to 1 or 2 stages. However, we believe that optimizing for a slightly larger number of steps can lead to better results. By combining a more conservative target with our improved sampler and annealed schedule, we achieve significant improvements in image quality, bridging the gap between standard diffusion and low-step diffusion-inspired methods. Previous studies have shown that deterministic samplers degrade more gracefully than stochastic samplers when limiting the number of sampling steps. Some approaches have introduced specialized architectures to distill knowledge from diffusion models into single-step models. Progressive distillation stages the distillation process, reducing the number of model evaluations during training and exponentially decreasing the required sampling steps with each stage. While methods like rectified flows and flow matching aim to reduce sampling times by mapping to a standard normal distribution, they often require many evaluation steps. Our experiments focus on quantitatively comparing FID scores on ImageNet and qualitatively assessing large-scale text-to-image models. By training diffusion models on ImageNet 64 and ImageNet 128 and base and large variants, initializing consistency models from pre-trained diffusion model weights, and utilizing consistency training and distillation, we observe considerable performance improvements as the multi-step count increases. This validates our hypothesis that more steps strike a beneficial balance between sample quality and speed. Annealing the step schedule proves crucial for achieving good performance, especially for low multi-step models. In comparison to existing literature, our approach achieves state-of-the-art FID scores on ImageNet 64 for 2-step, 4-step, and 8-step generation. We also achieve comparable performance using a single-step CD model compared to ICT Deep, which relies on direct consistency training. Our results suggest that multi-step consistency may be less sensitive to hyperparameter choices, highlighting the effectiveness of our approach in improving sample quality and performance. Section Summary. In this section, we compare our approach to existing works like consistency models and tract. Unlike consistency models, we propose operating on multiple stages to simplify modeling and enhance performance significantly. Our experiments demonstrate that increasing the number of steps in multi-step distillation leads to improved performance, closing the gap between sample quality of standard diffusion and low-step diffusion-inspired methods, achieving state-of-the-art FID scores on ImageNet datasets. Section: Qualitative Evaluation on Text-to-Image Modeling. In this section, we conducted a qualitative evaluation on text-to-image modeling. We didn't just rely on numbers from ImageNet. We also looked at how a text-to-image model performs by directly comparing examples. We began by training a large diffusion model with 20 billion parameters on pairs of text and images using AT5XXL paper for 1.3 million steps. Then, we simplified this model into a 16-step consistency model using the DDIM sampler. By comparing the samples from our simplified model to the original DDIM sampler with 100 steps, we noticed only minor differences. Although our simplified model sometimes captured specific details better, it came at a small cost to the overall structure. Another comparison we made was between a DDIM simplified model, similar to having eta equals 0 in a DDIM, and the standard DDIM sampler. Once again, we observed many similarities when starting from the same random seed.